Welcome to Chapter 18, Section 1. We're going to be talking about schematic diagrams and circuits. And our goals are to interpret and construct circuit diagrams. We're going to identify whether circuits are open or closed. And we're going to deduce or figure out the potential difference across a circuit load given the potential difference across a battery's terminals. So what we're really looking at and learning about is something called circuit diagrams. And another word for that is called schematic diagrams. So these two things, they really just mean the same thing. Okay, so don't be confused if you see it called a schematic diagram. And all that these do is these are a systematic or an organized way, okay, that we can show all the parts of a circuit so that anyone anywhere can understand a circuit and how it works. And most of these symbols that we're using are uniform throughout the electronic world. So anybody anywhere really can read your circuit, whether or not you're in the same country or even speak the same language. So let's look at some of these symbols. So wires are always drawn, and they will always have either straight lines, or if you need to bend or curve the wire, that will show them at right angles, okay? You never draw a curved line, okay? That's a big no-no. Resistors then, okay? Resistors we draw a straight line for the wire until we get to the resistor, and then the resistor symbol is just a zigzag shape, and then it continues into a wire. Okay, do make sure that it's zigzagged and not curved. Okay, because if it's too curved, then it's actually going to be something else. So you don't want to draw them like that. You want to draw it like this. The last one we're going to look at in this page is a light bulb. Okay, so a light bulb, the way it looks most of the time is we draw the straight line for the wire, and then it's going to come up, curve around, go back down, and continue on. But then we're going to add this little circle around it, and that helps us identify it as a light bulb and not something else. So those are the first three symbols to look at. Let's look at another three. The next three are a battery, a switch, and a capacitor. So a battery symbol looks like this. You have the wire that comes to it, and then you have a big line and a little line. And that would be one cell of a battery, so if you just had one battery, okay, or you might have multiple ones. Okay, and so you just keep alternating long and short sides, and then it continues on. The long side always represents the positive terminal, and the short side always represents the negative terminal. Okay, a switch has the wire, and then you draw a circle. Okay, and depending on whether the switch is open or closed, then we might have a line like this, and then continues. Okay, or if it's a closed circuit, we would just have the the circle's drawn that way. Okay, so this is what a switch looks like. And the last one is a capacitor. And a capacitor, remember, they're parallel plates most of the time, so we just draw it as though it were parallel plates. Sometimes you can also see it where one side will be curved, but most of the time for our class, we will use this version. So this identifies most of our sources. The last one I want to show you that's not in your book, but that we have used and we will see again is this symbol for a voltmeter, okay, which measures the voltage. You'll remember this from lab, and that we just use a big letter V inside of a circle. And the other one is the ammeter, right, which measures current. Okay, and that one we draw with a circle and the letter A. Okay. The only other symbol that we might use that's not on here is if we have an AC voltage source. Okay, that one will have a line and then a circle, okay, kind of like the meters, but what it'll have inside is this little kind of like a sine wave, and that represents that it's an AC source. So that covers most of the possible circuit symbols that we will see in this class. You do need to know these and memorize them because we will use them and you will be tested on it. All right, so now let's look at an actual electric circuit. Okay, so a set of electrical components, okay, that we put together and connect so there's at least one complete path for the movement of charges. Okay, this gives us an electric circuit. So we talked about this a little bit before. So the simplest kind of electrical circuit would be one where we have our battery, right? We've got the plus and the minus, We write the V next to it to represent that it has a certain amount of voltage. Okay, and then it will come up and it will go around, and we would have a resistor or a load of some sort and connect back. So do remember, the charges need to be able to flow in this complete path. Okay. If there were any gaps, it wouldn't work because the electric charges couldn't flow. Okay, and we represent this with the letter R, and we will almost always label what these components are because sometimes we might have more than one. The other thing I want to point out is, like I mentioned a minute ago, you notice I used right angles here. Okay, if I had drawn this circuit like this, okay, that would be incorrect, okay, because we must have these right angles here, okay, no curved lines. It's very important because as it gets more and more complicated, you want it to be clear, and I'll show you an example of a really complicated circuit here in a few minutes, okay. But I want to help you understand why it needs to be a complete circle in order for it to be a circuit, okay, and so that example is like thinking about water flowing. Okay, so imagine now that we're using water, and we have, we're going to have a pump. Okay, so I'm just going to make this box. This is a pump, and it pumps water, so it moves it around. Okay, so I'm going to use blue now for the water. So if we maybe have some pipes, okay, for our water to flow in, okay, so here are our pipes. Okay, this pump is going to push the water around. Okay, so it's going to make the water flow, flow, flow all the way around the circle, right? And without the pump, these wouldn't flow, just like without a voltage source, okay, our charges can't flow, right? So if we're working at this and we come along and we erase part of this, right, with water it might flow out, or maybe we even just draw it there, right? Even if this is pumping now, right, even if this is pumping, no water over here is going to really be moving, and no water here is really going to be moving. It's going to be stopped, right? So what we have to have, what we must have, is this ability for our water to flow, right? So we reconnect this so that it can go around. So really a circuit is very similar to having water flowing, right? You have to have somewhere that it can go, and it must be able to travel all the way around, okay? So this is very similar to the way a circuit works. So if we take a closer look, we can have many different options, but what we must always have is what we call closed loops. And this is for the reason I was just talking about. Okay, so we can have circuits like the simple one we saw just a minute ago where I have a battery. Okay, and this time I'm going to have 2 cells just for fun. And our resistor. Okay, this is a very simple one, and we have one loop. And it's a closed loop because all of my current, right, can flow all the way around. Okay, and I've got my voltage and my resistor. But we can actually have any number of loops as possible. Okay. Okay, any number of loops. There's no limit to that, actually. You can have an infinite number of loops. Well, maybe not infinite, but very close. Okay, so if I drew just one step up and I created 2 loops with this would look something like this. Okay, so I've got my voltage source here, and then I've got one resistor on it. Okay, but then I can add another resistor. Okay, and I could even put a resistor out here. Okay, so now I've got multiple paths, and so this is resistor 1, resistor 2, resistor 3. We could add capacitors, we could add light bulbs, we could add a whole bunch of different things, okay? Right, but we're creating these loops for current to flow because we could have one loop there, we can have another loop there, and we can have another loop here even. Okay, so this one has 3 loops for the current to flow through. Okay, so any number of loops is really possible for as long as they are closed loops that allows our current to flow. Okay, this word flow is a key idea here. So with that then, okay, here's a simple, a slightly more complicated but still simple example of a circuit. Okay, and this has, I want you to pay attention that all these angles are right angles. Okay, these dots just mean that they're connections. Okay, And some of these other symbols you see, we're not going to worry about what they mean, but there's a whole bunch of other things that you can put into circuits. But we can identify some capacitors here that they labeled as C1, C2, C3. We see some resistors, okay, among other things. Now we can actually take this and, computers and phones and everything, these all have electronics, and they can get quite complicated. Okay, so here there's a whole bunch of things. Some of them I don't even know what they mean, but you can still see some things that we recognize, right? Like this R2 represents a resistor. They've made them boxes in this case. You can still see capacitors here. Okay, so way down in the corner down here, right? This is a voltage source. But we have all these different things all over representing different items. Okay, we've got more voltages over here. And so circuits can get really complicated, but we're just going to look at very basic, simple ones. If you're doing stuff like this, you're probably studying something like maybe electrical engineering, okay, or computers or something like that. Okay, so if you think this is cool, go study electrical engineering. So let's take a look at how we draw a circuit from reality, because it's all really nice on paper, but being able to identify it and draw what was really going on is really what the point of this is. So you may recognize this circuit from class. We have the voltmeter that we looked at. We have our voltage source. We've got our ammeter that measures the current. And right here, don't forget that is our resistor. Okay, so what we're going to do is I want us to look at this and see if we can kind of figure out how the circuit goes. So I took the picture so that we don't see any wires overlapping, right? But they are kind of curling around all over the place. And them curling around is kind of what makes it confusing. Okay. So this is why we draw circuit diagrams, because even if we could take pictures of circuits all the time and send them, they could potentially still be really complicated. Okay, so what I'm going to do is use this blue pen here, and we're just going to draw this circuit, and we're going to draw it oriented like it is. So we start up here with a voltage source. Okay, and I'm going to draw it like a battery in this case. Okay, although we could actually draw it some other ways sometimes too. So I've got my positive terminal here and my negative terminal here. Okay, and then the next thing, right, we follow this wire, it connects us to our ammeter here, which remember I told us the symbol for that is the letter A. Okay, so I'm going to draw this. Okay, and I'm just going to connect it to this ammeter. Okay, so I've used a straight line because we can't have any curves. If we keep following this wire around, right, we're going to come down to our resistor. Okay, so what I'm going to do actually is I'm going to come down. I'm going to go at a right angle. Okay, and I'm going to pull my resistor back in here. So these right angles, they don't actually mean anything. It's just a way for me to almost draw a curve, but we just draw it at right angles to help things be clear. Okay. And now if I keep following this loop, right, I can actually go through the resistor and come back to the positive terminal of the voltage source. So I can keep drawing this line, come up, and reconnect it. Okay, and make sure these lines all the way connect. So now what I have here is I have my resistor, I have my ammeter, and I have my battery, okay, or my voltage source. So then the next step is to just add this voltmeter in, okay? So I take that, and to make things simple, I'm just going to connect it here. Whether I connect it here or if I wanted to draw the line here, either would be okay. But usually if there's nothing else or no reason to draw it closer, we would just draw it there because it looks nicer. So we're going to draw that down, and then we have our voltmeter, and then we're going to draw it back up and connect it because it connects to the other side of the resistor. So this here then is the circuit diagram or schematic diagram. Whoops, I can't spell. Let's erase that. Oh, whoops, accidentally erased too much. Let's put that back really fast. Okay, so this is our circuit diagram. Of our real circuit. And really you can see, compared to all these wires squiggling and going all over the place, this really looks much clearer once you learn how to identify all of these different circuit pieces. Okay. So now I want to talk about an open versus closed circuit, okay, because open means current can flow, or excuse me, can't flow. Okay, so current cannot flow. Okay, and closed means current can flow. So we just call those open circuits and closed circuits. Okay, so open circuit would be one where maybe we have our resistor, okay, and now we've added a switch that is open, okay, and then we have our voltage source. And sorry, it's a little hard to make these look perfectly closed actually, drawing on my screen here. Okay, so imagine all those wires connect. So here we've got an open circuit, we've got a gap, so current cannot flow. We do not have a closed loop. Current will then flow in the same circuit. Okay. If we then just draw the switch as closed. Okay, and it's essentially like turning things on and off. So here we have a closed loop, so the current can flow. Here, the current does not flow. Okay. So that's the main difference. When you see open and closed circuits, that is all that they are meaning. So one of the last things almost that I want to look at is something called a short circuit. Okay, so a short circuit happens when wires connect across a voltage source but has no load. And load is just something that draws energy and can mean it has no resistance. If it has no load, you have no resistance. And this can be very dangerous because wires often overheat and cause fires. So an example of a diagram where you have a short circuit would be one where, let's say we have our battery, okay, and we connect it to a resistor. Okay, but now maybe insulation is broken, or we take a wire and we connect it across here. Okay, so what's going to happen is the current wants to all flow through this because there's no resistance here. Okay, and so all the current that way, and because there's resistor here, almost no current will flow through that. So all the current will go through here, and this can often cause it can be dangerous because it will cause the wires to overheat, which can then cause fires. So another way to think about this, if we go back to our water flowing example, right? Imagine we have our pump again, okay? So here's our pump, and it's pumping water around, right? So we've got our pipes, okay? And it's pumping the water through. Okay, so now imagine that we take one of these wires and we make it go uphill, right? But we still have this one here that's not uphill. This one's flat, okay? And we're trying to pump the water around, and maybe uphill's where we want to get it because it's going to come and do work when it comes back downhill. But the reality is, if you have this pump, as long as this is big enough and this is easy for it to flow, all the water is going to do this. None of the water is going to go uphill because it can all go flat. That's so much easier. Okay, so this is the same thing with our circuit. If you have the short circuit, right, so let's just draw our circuit again really fast, right? If you have the short circuit, right, there's no resistance. So all the current, all the charges are going to flow through that area versus if you add a resistor. Okay, they don't want to go up here. This is like going uphill. Right, so a resistor is like traveling uphill, and this short circuit area, right, this is like going in a flat space. Okay, so that's why short circuits can be dangerous, because they'll do that, there's no resistance, you get lots and lots of heat, and you might start fires or break your device or other things like that. So the last thing we're going to talk about is just kind of a couple definitions. So I just want you to be aware of this word EMF. Okay, so EMF stands for electromotive force. And it's anything that supplies a potential difference and essentially pumps, to use the words we were just using, it pumps charges around a circuit. Okay, so a battery is an example of an EMF source. Plugging into your wall and getting electricity that way is being supplied by an EMF source. So that you should just recognize what EMF means. Okay. So with that, I just want to differentiate and point out something here. So inside of a battery, okay, there's actually a small amount of resistance within the battery itself, right? So if we drew a picture of a battery, okay, and this is our AA battery or something like that, right? This, maybe it says it is 1.5 volts, okay? So, but inside the battery, what we really have is, like, you could imagine like another battery inside of it, okay? And then a little bit of resistance, okay? And then this is what actually will connect around to our circuit. And maybe we're connecting a light bulb. We haven't drawn any of those. Okay. And this has, right, a resistance as well. Okay. So what this does is it actually reduces the voltage that we measure across the battery. So this is really what is 1.5 volts. Okay, but maybe if we actually measured this, right, if we measured it at the terminals, what we might find is it's actually 1.4 volts because of this little bit of internal resistance. Okay, so this small amount of resistance means the voltage measured across the terminals, right, the terminals are the ends, okay, is slightly less than its stated EMF. Okay, and so this is called its terminal voltage, and terminal voltage is always a little bit less. So this is terminal voltage here. Okay. However, knowing that whenever we talk about batteries, it's important that you know this fact about batteries, but when we talk about them in circuit diagrams, we're going to ignore this difference, okay? So that means if I tell you that you have a 9-volt battery, okay, connected to a resistor, you can assume that it is indeed 9 volts. And so if we just draw our quick circuit diagram again here, okay, I would say that this is 9 volts. I'm not going to say it's like 8.8 or anything like that. Okay, we're just going to assume that it's actually giving 9 volts to our resistor. So that brings us to the end of section 1. Go ahead and let me know if you have any questions in class, and I will see you guys there.